Hello again. Let's talk about the connection between, let me grab a pen here, between electric field and electric potential. They're related. Big surprise in a rather interesting way. Okay, so if we take a charge and we move it through an electric field, the work we do on the charge is the force times the displacement. Brain fart. The force, of course, is equal to the magnitude of the electric force. Okay, but in the opposite direction. If we're doing work against, we're moving it in an electric field. There's an electric force on it from the field. We are applying a force opposite to that. And so we have our applied force is the opposite of the electric force, which can be calculated by multiplying the charge by the field strength at that point. Okay, and finally, we learned that work in moving a charge Q through a potential delta V is Q delta V. Oh, God. Big surprise. Okay. Fantastic. Now, we want to put this all together to come up with the relationship between electric field and potential. Okay, so I'm going to start here. I'm going to write this equation again. Work equals force times displacement. And then I'm going to make some substitutions. Okay, work, I'm going to put in Q delta V, charge times the potential difference. That's the work done, moving this charge through a potential difference in an electric field. And then the force is our applied force is the opposite of the electric force, which is the charge times the field strength. And then multiply that force by the displacement. There we go. And so we have, they all brought Q to the party, so we can divide out the Q. And we get the potential difference is equal to the opposite of the field strength times the displacement. And if I solve that for the field strength, I'm going to get this nifty equation. The electric field strength is equal to the opposite of the potential difference divided by the displacement. This is a rate of change. It's the slope of something, right? Or it's, as we like to say in IB physics, it's the gradient. Okay, so this electric field, this is a gradient. That's the gradient of the potential, right? It's the rate at which the potential changes with respect to x, a displacement. All right, and so the electric field is the opposite. The electric field strength is the opposite of the potential gradient. Okay, so what does that mean? It means that the electric field strength at a point gives you an indication of how quickly the electric field is changing, right? The electric potential is changing. I'm sorry. A greater field strength indicates that the potential is changing much more rapidly for a unit change in distance. A lower electric field intensity means that the potential is not changing as quickly for a given unit displacement. All right. So there you go. Electric field is opposite of the potential gradient. That's how they're related. Okay, let's talk about this. Talk about the potential and electric field at a point when we have some charge evenly distributed on a conductor. Okay, let's get another page here. All right, so we have a. Let me grab. I can actually do shapes. I don't have to hand draw shapes. Excuse me. We have a charged a conductor with a charge on it. The charge will all reside on the surface. As we know, one of the charges is not like the others. It wants to be an X, not a plus. Okay, so we have this. That is the radius of the sphere. Okay, now outside the sphere, we know that we can consider the charged sphere to be a point charge with all of the charges on the sphere concentrated at the center. Okay, so out here, the potential is going to be just what it normally is. KQ over R, right? That's the potential. And the electric field, let's do the electric field in another color. The electric field will be KQ over R squared, right? Electric field is the charge times the electric force. That's Q times K, QQ over R squared. And so those divide out. We have just K big Q over R squared. There's our electric field strength. Okay, fantastic. There we go. Okay, so outside the field is, and we're going to build a graph here of potential. And we're going to build a graph of field strength. Okay? So in the normal way, wait a minute. Oh, I can do fancy stuff here. I can do a line with no endpoints. I can make it dashed. And I can do this. Except I don't want it in black. I don't want it that heavy either. Okay, I'm playing with my, I haven't used this software in the longest time. So, since smartboards, right? So that was before COVID. There we go, and there we go. Okay, now back to our regularly scheduled program. So outside the sphere, okay, we have right? That's our graph. That's KQ over R. And for the electric field, we have similar thing. Okay. KQ over R squared. All right. Same shape. Okay. Now, let's talk about the field and the potential at the surface of the sphere. Okay, so the electric field at the surface of the sphere, right at R naught, will be it will just be K Q R naught squared, right, which is just this value right here. Fantastic. I wonder, hang on a second, I want to try and do something. Where's my selection tool? I don't know. Transparency? No, that's lines. Here we go. All right, never mind, I can't do that. Back to the physics. Okay, so that's the electric field. The potential at the surface, right, is the potential difference at the surface is 0. There's no change in potential. The surface is all at the same potential, right? So there's no change in potential at the surface. And so that becomes, at the surface, that potential, maybe I should use the tool to draw a straight line, since my lines are not good. That's still black and a curvy line. Let's go red. Let's go with a solid line. And there we go. The potential drops to 0. Okay. And hang on, I want to try something here. There we go. Okay, good. And I'll take my eraser and clean this up. There we go. I just want to make the axes. Okay, that way my pen is going to stand out when I draw. Okay. Good. Sorry. Okay, so there we go. So the potential of the surface drops to 0. All right. The field at the surface is KQ over R naught squared. All right. And the potential is 0. 0 for the potential. KQ over R naught squared for the electric field. And then when we get inside, what happens? Well, inside, there's no electric field, right? Inside, the boy, I've screwed this up pretty big time. Inside, there's no electric field. At the surface, since the potential is the same at the surface, you knew we couldn't get through one of these without Susan making a mistake. So let's back up. I know you've got to erase all kinds of stuff in your notes now, assuming you're taking notes. The potential is the same at the surface, okay? Everywhere on the surface, the potential is the same. The charge is evenly distributed, and so the potential is the same. Hang on, I'm trying to get rid of this red line. There we go. Okay. So it's the electric field that drops to 0. It's the electric field that drops to 0. Oh, for gosh sakes. Blue. Thin. The electric field drops to 0 at the surface. Why does the electric field drop to 0 at the surface? If there's no change in potential, right? If there's no change in potential, then the potential gradient is 0, which means the electric field is 0. Okay? So it's the electric field that drops to 0. Let's see if it has done what I want it to do. Yes. Yes. Okay. So it's the electric field that drops to 0. All right. Fantastic. And then what about the potential? The potential at the surface is, the potential is KQ over R naught, right? So the potential at the surface will be KQ over R naught. That's fine. It's the electric field that goes to 0 because there's no change, there's no gradient, there's no potential gradient. Potential is the same. And inside the sphere, the potential is the same everywhere. Again, right? There's no, as I go from this point on the surface to this point on the surface, there's no change in potential. Okay? So inside, the potential is the same everywhere. It's still, I should do it in red. Inside, it's still KQ over R. are not, right? And since the potential is not changing inside the sphere, the electric field, again, is zero. There's no gradient, right? So that means the electric field is zero inside the sphere, and the potential is constant. Okay? So that's what boy, that took way longer than it should have. I apologize for the rambling and so forth. Okay, let's say a few more things about potential. I'm going to go to a new page, so you pause if you need to get these notes down. Here's the new page. Equipotential lines are lines of equal potential, where the potential doesn't change. So we just saw that on a sphere, on a charged sphere, the surface of the sphere is at the same potential. That's an equipotential line. Okay? And we look at the field lines. I'm going to draw the field lines radiating out from this okay, field lines. In just a second here, I'll get some field lines out there for you. Okay. So the surface of this sphere is at the same potential. Okay. Now I just want to remind us that for field lines, field strength is proportional to the density of lines. Right? How close together the lines are. Increased density of lines, increased field strength. Decreased density of lines, decreased field strength. Okay. So here at the surface, those field lines are all the same distance apart, right? Same density of lines. That's an equipotential surface. If we come out here, okay, where we have a new potential, if I draw a circle, let's see if I can do this here. I'm going to draw a blue circle, fill color, none, line color, blue, line weight, 1. There we go. That's a circle. Every point on that circle is the same distance from the charged surface. And if you go around that circle, the density of those field lines, right, is the same all the way around the circle. That means the field strength is the same all around the circle, right? And the field strength, remember, is the opposite of the potential gradient. Okay? And so what we have here, let me do this. Yep, that's supposed to be a negative sign. Sorry. Undo. Okay, so opposite of E delta X. Okay, so the electric field strength is the same around here. The distance from the surface is the same. And so the potential difference going from the surface to this point is going to be the same for every point on that circle. Okay, so that circle is an equipotential surface. The potential is the same at every point on that circle. Equipotential line. Or actually it's a sphere, so it'll be a surface. It'll be an equipotential surface. Okay, and I could go and I could make another circle. Let's see if it's still blue. It's still thin. It's still blue. I could make another circle. And if I'd done it right, and it was concentric, that's another equipotential. There's another one. So all these spheres that are concentric with this charged sphere are equipotential surfaces. Okay? All right, just a couple more things to say, and then we're done with this really long video that doesn't say much. So work done is equal to the change in potential times the charge, right? So moving a charge along an equipotential line or an equipotential surface requires no work because there's no change in potential, right? Work. Oh, let me grab a pen here. Work equals Q delta V. If delta V is 0, then the work is 0. Okay? I don't know if we talked about this last year. Conservative forces and conservative fields. Gravity is a conservative force. The path doesn't matter. The work is done. Moving between 2 points in a gravitational field, the work is the same no matter what path you take. Okay, that's called a conservative force. Electric force, is a conservative force. And the path you take to go from one potential line, from one potential to another, doesn't matter. We'll talk about that a little more. That's a subtle point. And I just want to point out one more thing. You'll notice that these equipotential lines are perpendicular to the field lines. Okay? Where the equipotential lines intersect the field lines, they're perpendicular, and that's always true. So if I had a uniform field, okay, if I had 2 plates, and there's a uniform field in between, and if I want to do field lines, then go with blue, right? Field lines. Well, they'd be evenly spaced. They're not here, but I'm doing the best I can. Those are my field lines. The equipotential lines are going to be these red lines. Okay? These are the equipotential lines. Oop, they almost came in too thick. They're going to be perpendicular. And so the equipotential lines are going to form a grid like this. They're all going to be perpendicular to field lines. Okay? And so we've got this potential ladder between the plates, if you will. Okay? So there's that. What else did I want to say? I think that's about it. There's some different plots in your notes. You can take a look at those. But I think that about wraps it up for electric potential. Okay? Alrighty. Goodbye.